This morning, I'd like to talk about two different ways that you can sometimes see that an infinite series converges or diverges. These are based on limits and direct comparisons of individual terms. What we'll call the direct comparison test is this. Suppose you have a collection of numbers, AI and BI. All of these numbers are positive. And not only that, you know that the AIs are no more than the BIs. Then it's going to be possible to show, as we'll see in a moment, that this statement is true if the sum of the terms on the outside here converges. Then the sum of the terms on the inside converges as well. There's an equivalent statement that we can get based on the contrapositive for free. The contrapositive is if the sum of the AIs fails to converge, if the sum of the AIs diverge, then it's untrue that the sum of the BI converges. If the sum of the AIs diverge, then the sum of the BIs diverges also. The reason for that is not very difficult to see. Since the individual B numbers are positive and the infinite series of the B numbers converges, let's say to some number capital B, any partial sum of the B series can't be larger than or equal to capital B, because if it was, any later partial sum of the B series would be larger than B, and there would be no way to get the partial sums to approach B then. Based on that idea, think about the first k of the inequalities that we have. We're going to add these things together. This shows that the collection of partial sums of the A series is bounded. All such partial sums are at least zero, and none of them are larger than the corresponding partial sum of the B series, which in turn is less than B. On the other hand, if you were to add additional terms in the partial sum for the A series, those partial sums will increase because the A's are positive. This means that the sequence of partial sums for the A series is increasing and yet bounded at the same time, and an increasing bounded sequence converges. This proves the first statement that we were looking at. The second statement is logically equivalent to it. Under certain circumstances, this makes it very easy to decide if a series converges or not. Think about the sum n equal 1 to infinity, 1 over n squared plus 5n plus 1. The terms that are getting added together in the bottoms of the fractions are all positive. When you make the denominator of a fraction larger, you make the fraction smaller. So the following statement is obviously true. It must be true that 0 is less than 1 over n squared plus 5n plus 1, which is certainly less than or equal to 1 over n squared. We know that the sum 1 over n squared converges since it's a p-series with p equal 2. Then the direct comparison test says the infinite series that we're interested in converges. We need to be able to write down this kind of thought very precisely. Since 0 is less than 1 over n squared plus 5n plus 1, which is less than or equal to 1 over n squared, and the sum n equal 1 to infinity 1 over n squared is convergent, as it is a p-series with p equal 2, the direct comparison test tells us that the sum n equal 1 to infinity 1 over n squared plus 5n plus 1 converges. Part of developing some mathematical maturity is being able to say in this way exactly what you mean. Leave nothing out that's important, but on the other hand, don't say things that don't need to be said either. For the series, the sum n equal 1 to infinity, cosine squared n over n cubed, all we have to do is observe two things. Firstly, the cosine function never exceeds 1 or negative 1 in its range of values. When you square a number, you lose any negativity that it might have had. Cosine squared n can't be negative. It also can't be larger than 1. I can divide through by the positive number n cubed and find out that cosine squared n over n cubed is between 0 and 1 over n cubed. If I wanted to write out a sentence as I did before, I would say that since this inequality is true, and the sum n equal 1 to infinity of 1 over n cubed converges, it being a p-series with p equal 3, it follows that the sum n equal 1 to infinity of the terms in the middle, cosine squared n over n cubed, converge by the direct comparison test. In looking at the sum n equal 1 to infinity 1 over n squared minus 10, this is very similar looking to what we just did a moment ago, but this time there are a couple of issues. Firstly, if you look at the n equal 1, n equal 2, and n equal 3 terms, you'll see that they're not positive. After that, all terms are positive, though. We have previously decided that convergence or divergence of an infinite series is not affected by altering the first few terms of it, though. So the fact that the first few terms are negative does not disturb me. Since square root of 10 isn't a whole number, we at least don't get division by 0, so all of these numbers make sense. My problem now is that the inequality goes the wrong way for a direct use of what we've been talking about. After a while, after n is 3, n squared minus 10 will be positive, n squared minus 10 will be less than or equal to n squared. In an inequality, I can divide through by a positive number and not alter the inequality signs any. Doing the algebra, I found out that 0 is less than 1 over n squared, which is less than or equal to 1 over n squared minus 10, and this is very unfortunate. If you look at the statement of the direct comparison test, what it says is, if the sum of these terms converge, then I guarantee you that the sum of those terms converge. At the moment, I don't know if the sum of those converge or not, so this really doesn't tell me anything. I do not have a statement that says, if the sum of those things converge, then the sum of these things converge. If I did, I'd be in luck. The other half of the statement, the direct comparison test, says, if the sum of these things diverge, then I can draw a conclusion. Unfortunately, the sum of 1 over n squared doesn't diverge. It converges because that would be a p-series with p equal 2. The statement of the direct comparison test as it stands right now doesn't tell me anything if this is how I'm trying to think about my problem. What I really need is an inequality that looks like this, except the n squared needs to be in the middle and the n squared minus 10 needs to be on the outside. Now, that's never true, though, because n squared minus 10 is never bigger than n squared. But on the other hand, if n were very, very large, then I think that n squared minus 10 would be a substantial fraction of n squared. I bet that after a while, n squared minus 10 is more than half of n squared. Now, this is just what I think. I have to verify this conjecture of mine. So let's see what we can do. I want to see under what circumstances n squared minus 10 is bigger than 1 half n squared. The 1 half is just for convenience. I could have used 1/3 or 1/4 or 0.9. I could use any number that's not as big as 1. What I'm hoping to see is that this is going to be true for all n values beyond some specific n value. Multiplying through by 2, I find out that 2n squared minus 20 should be larger than or equal to n squared. Subtracting n squared from both sides, I find out that n squared minus 20 should be bigger than or equal to 0, meaning that n squared needs to be at least 20, meaning n needs to be at least radical 20. N is going to be a whole number, though, and radical 20 isn't. So certainly if n is bigger than 5, then n is bigger than square root of 20. After you get past index 5, this inequality is true. So I'll think of only looking at terms within bigger than 5. Having done that, n squared minus 10 and 1 half n squared are positive. I can do the same manipulations as before and find out that if n is bigger than 5, then 0 is less than 1 over n squared minus 10, which is less than or equal to 2 over n squared. These numbers are 2 times 1 over n squared. It's twice the term of a convergent p-series. So the sum of these things converge, which tells me the sum of these things converge by the direct comparison test. A purist will object that I have to assume that n is at least 5 here, so that if you wanted to be picky about it, all we really convinced ourselves of is that the sum n equals 6 to infinity, 1 over n squared minus 10 converges, but this is no problem. That series is the same as the series that we've actually been interested in, except terms where n equals 1, 2, 3, 4, or 5 have been deleted or set equal to 0. Changing a finite number of terms in an infinite series doesn't change whether it converges or not. So the moment that I know that this converges, I know that that converges as well. Even so, working directly with the direct comparison test can be kind of painful. So we have another one that we want to look at as well. In what we're going to call the limit comparison test, we have two series which are based on adding up the AI numbers and BI numbers, which are all positive, at least after a while anyway. We look at the limit as I tends to infinity of AI over BI, call that limit L. If L is finite and not zero, then the infinite series based on the A numbers and the infinite series based on the B numbers both converge or both diverge. In this case, there's no need to worry about which of the AIs and BIs are larger than the other one. So in many cases, this is more convenient to use. Let's suppose that this is the case. What does it mean for the limit as I tends to infinity of AI over BI to be equal to L? It means that beyond a certain index, AI over BI must be close to L. Beyond a certain index, AI over BI can't be any further away from L than 1 unit of distance, or a half of a unit, or 10 units. Pick any number that's convenient for you. Beyond a certain index, it certainly has to be true that AI over BI, which is positive, is less than the constant number L plus 1. Since BI is positive, you can multiply through by it. And then we can apply the direct comparison test. If the sum of the BI's converge, then so does a constant times the sum of the BI's. The direct comparison test tells me that the sum of the AI's converge. On the other hand, the logical contrapositive of that is if the sum of the AI's diverge, then the sum of the BI's diverge, and we have half of our result once again. The numbers BI over AI are the reciprocals of AI over BI. These numbers get close to L. Their reciprocals must get close to 1 over L. This is the part where I need the limit to not be 0. Beyond a certain index, though, all of the BI over AI quantities must be smaller than 1 more than 1 over L. Then, since the AIs are positive, multiply through by the AIs. And then we play the same game as before. If the sum of the AIs converge, meaning that the sum of these things converges, the direct comparison test tells me the sum in the middle converges. If the sum of the AIs converge, the sum of the BIs converge. And then, logically equivalent, if the sum of the BIs diverges, then so does the sum of the AIs. This is the limit comparison test. So let's go back and look at the sum n equal 1 to infinity, 1 over n squared minus 10 again. After a while, all of those terms are positive. And also, we mentioned previously, after a while, there's a very strong resemblance to 1 over n squared. So what we'll do is we'll use the limit comparison test. The term out of one of my series is 1 over n squared minus 10. The other one is 1 over n squared. If I calculate the fraction of those two terms, take the limit as the index tends to infinity, and the result comes up a positive finite number, then I can draw a conclusion. Let's look at the sum, n equal 1 to infinity, 1 over n squared minus 10. When n is very large, the individual terms strongly resemble 1 over n squared, so I'll use that for my comparison series. Doing the algebra and taking the limit, we end up with a value of 1. 1 is positive and finite, so the conditions under which the limit comparison test will tell us something are satisfied. If I wanted to use careful language here, I would say since the sum n equal 1 to infinity, 1 over n squared is a convergent p-series, p is 2, the limit comparison test tells us that the sum n equal 1 to infinity, 1 over n squared minus 10 converges. And you'll note I didn't say anything that I didn't need to say, and just enough to tell everything that's relevant. A roadmap of where we've been so far with this subject is we initially talked about sequences, which led us into the idea of infinite series, in particular geometric series, the discovery that the harmonic series diverges, telescoping series. Then we looked at the integral test, most recently the direct comparison test and the limit comparison test. Next, we're going to take a little side trip and talk about something called alternating series. This will be a natural segue into the notion of absolute convergence. This will allow us to think about something called the root test and the ratio test. Then we will talk a little bit about Taylor and Maclaurin polynomials, and finally, power series. I hope that everybody's having a good day. I'll talk to you again soon.